All right, so this is Module 3 for Lecture 22 in our Section 4, Advanced Supervised Classifier. So we have covered about tree representation for classifiers in the Module 1, and then we covered about using information theorem grounded measure to split node to get decision tree representation. And now in the Module 3, we will review the bootstrapping and how to use Bootstrap to get backed version of decision trees. Okay, so let's get started.
So the simplest strategy is to remove the high variance of a high variance model and is something called bagging. The bagging relies on Bootstrap. So I hope you already learned it in your statistics basic entrance class. So Bootstrap in the end is just sample, right? You sample from a set of training examples in our case, and use each sample to train a tree. And then you build a committee of different trees, and then together they make predictions by majority voting. So for instance, each tree casts a vote for the predicted class, and then you can grow like B trees based on B different bootstrap of your training samples. And it's a very classic technique for reducing the variance, the bootstrap. So the specific bootstrap used in the bagging is called bootstrap with replacement. So which means if I sample a point from the original training set, I got it from I sampled it in my bootstrap set, but then I'm going to put it back. And then I'm going to sample again. So which means I may get duplicate of a specific sample maybe twice or a few times because I put it back and then I'm doing resample. So this is called bootstrap with replacement. Question about this. Bootstrap with replacement. And the whole point is I want to get my new training set as the same size as my original training set. So this here's a you can calculate the variance, but I'm going to skip that. So bootstrap with replacement can keep the sampling size the same as the original size for every repeated sampling. The sample data groups are independent on each other. So it's not conditional, okay, because I put it back, right? So every time I'm sampling a specific, the chance I got a specific training sample, it doesn't rely on what I get in my previous sample, right? Because every time I'm facing exactly n training samples, I just random sample. All right. Then it's very easy. So for the first from that training set with n samples, you bootstrap got the first bootstrap 1, which has a size n, then you got second bootstrap n, and then so on and so forth. You got B, different bootstrap repetitions from your training data. I should say not repetition. B bootstrap sampling from your training data. On each, you grow a tree. And then when there's a new testing data, you feed the data into each of the trees, and then you use the majority voting from all the B trees as the final decision. So this is called bagging trees. Okay, I think, so it's already 15. So there's the reason why we do this is, in fact, the instability of decision tree is good. It's good for the purpose of bagging. Because if it's a very stable classifier, there's really not much variations. And whatever you're bagging, you're doing the same thing. So for example, SVM, if you have small stability on the margin and you always, you got similar margin separations, right? So no matter how many B committee, B type of repetition, B bootstrap sample training set you get, you're going to get very similar margin bands. So even if you put all of them together, they're doing the same thing. They're doing the similar type of decision. It really doesn't make a point at all to perform bagging on those stable classifiers. But this instability of decision tree create a lot of variation and diversity and for the bagging to explore. So that's why bagging and decision tree create such a good team together. So we're going to talk about a lot more, much more advanced. It's called ensemble. So bagging is the simplest ensemble ever. So next class, we're going to talk about more guided ensemble. There are a lot of variations about ensemble approach.